for today, for this course. Osvaldo is not here today, unfortunately, he's busy, but he asked me to start at least one lecture with a couple of Russian words. So, hello everybody, привет, как дела? Are you alright? Let's start the lecture. Some aspects of philosophy of mathematics, use of visualizations and thought experiments. Today is going to be a very hard material, and I'm glad that I have the strongest in our group. So I'll do my best to explain everything as clear as possible, although in terms of mathematics it cannot be done in full details in the frameworks of our lectures. But I will give you enough of explanation to understand the philosophical points. So, as I said before, the focus of our course is mathematical practice, current mathematics, and the role of cognitive representations and thought experiments. So, in the last lecture, we drew some main characteristics of thought experiments, such as experimental character of thought experiments, experimental scenario, and also perceptual experience and presence of diagrams and visualizations. And I put in a little lie here for you to sort of to keep an eye on this point in your mind, because I will try to give some kind of explanation why in thought experiments we often have visualizations. So this is, I hope, something new which come up from our discussion. And mathematical thought experiments we decided to defined as something which goes beyond the mathematical rules, the traditional mathematical rules, and also something experiments which have imagination involving perceptual experience, sensory experience, some physical properties. And this I find interesting, that in such an abstract area of knowledge as mathematics, somehow we deal with physical properties and physical actions, although in imagination. And we were talking about epistemic roles of thought experiments. So the idea is that we can get some new knowledge from thought experiments. Brown and Laktush would say that thought experiments are proofs and refutations, and Norton would say that they are simply illustrations, they have only pedagogical role and no epistemic role at all. They are hidden arguments, and these are two extreme positions in terms of epistemic roles of thought experiments. However, I am trying to suggest that there could be other rules of thought experiments in mathematics. For example, discovery of new properties of mathematical objects, development of concepts, and connecting domains. Because there is connecting domains here, I want to contrast my case study on the basis of two dimensions. One dimension is, of course, mathematical and cognitive representations. Well, because we are talking about cognitive representations, right? Thought experiments, visualizations, they are cognitive representations of abstract mathematical objects. And the second dimension I want to contrast algebraic and geometric approaches. Because I mentioned that the cognitive representations can have important role in connections, domains within mathematical knowledge. Let me remind you that concerning the first dimension, mathematical and cognitive representations, mathematically a point on a plane can be represented by an ordered pair of numbers. So we have a point, well, here in 3 dimensions, not on a plane, in 3 dimensions, we have a point, and in coordinate system it can be represented into numbers A, B, C. Yeah? This is a mathematical representation of one mathematical object by another. The first object is a point, a geometric object, and the second object is a triple here of numbers. Cognitively, it can be represented as a dot on the drawing. So I hope you grasp this difference. And mathematical representations, once more I'm saying that one mathematical object can represent another one, and here I give some examples of mathematical representations. Groups, we studied groups last time, we were discussing groups, can be represented as generated groups, remember, if you remember, which actually means sets of words in generators with the composition function, the operation of the group composition. For those who didn't attend the previous lecture, we'll come back to this material. And generated groups can be represented by Cayley graphs. Again, we will discuss it later. And the new thing I will explain you today is that Cayley graphs, and therefore generated groups, and therefore groups, can be represented as metric spaces. Cognitively, we have, for cognitive representations of mathematical objects, we can have notations, formulas, tables, diagrams, all these perceptual, visual objects. Now let me move to the second contrast between algebra and geometry. Of course, everything I will say about this contrast is very imprecise. It's very rough. It's just for the sake of our case study. Of course, today's algebra and geometry merge. In modern mathematics, everything is merging. Areas are connecting with each other. But traditionally, historically, geometry, from the word geometry, it comes from Greek words geo, which is earth, and metron, which is measurement. So traditionally, geometry is conceived as a science of measuring earth. Whereas algebra comes from Arabic al-jabr, which is repositioning. Something what we do when we move one term of an equation to the other side and change the sign. For example, we have an equation 5 plus x equals 7, and we just rearrange it to x equals 7 minus 5. There is a typo here, minus 5. You know what I'm talking about. Yeah, solving equations. And one of the first algebraic textbook is here is a photograph of it. Science of transposition and cancellation. So algebra is really about this kind of manipulations, moving things, transforming objects from one side of equation to another side of equation, and then cancelling things which appear in both parts of equation. So this book has been written in 825 AD by Musa al-Khwarizmi. That's where we are getting the word algorithm from his surname, actually. And this is this is a stamp, actually a Soviet stamp, devoted to 1200 anniversary of this Arabic mathematician. So I thought this is how a Russian Cyrillic alphabet looks like, if you don't know. Again, in this second dimension, traditional subjects of algebra and mathematics, algebra and geometry are, in algebra, you are traditionally deal with, not always of course, yeah, but traditionally, you deal with discrete objects which are out of space, yeah, equations are not placed, not embedded in some spaces, sets relations between discrete objects. Whereas in geometry, you are usually dealing with continuous things, lines, triangles, figures, which are embedded in some space, Euclidean or non-Euclidean. You can measure things in terms of lengths, and they have spatial relations and things like properties such as curvature, for example. Well, I hope you know all this. And I put both dimensions in one table now: mathematical representations, cognitive representations, algebra and geometry. And I put a couple of very simple examples. An ordered pair of numbers in algebra can be cognitively represented in this way. I mean, that's how we denote it. That's how we write it down in our textbooks. A set of ordered pairs, we can write it as R, yeah. And a point in geometry, it would be a point on the plane and a line, and cognitively they would be represented as a dot and a line. Well, this is another table, maybe more examples. So again, mathematical and cognitive representations, algebraic and geometric. So in algebra, we are dealing with sets, relations, groups, rings, fields. Well, so far we know groups. Whereas in geometry, we are dealing with lines, figures, transformations, symmetries, spaces. And algebra operates with symbols, lists of symbols, tables, matrices, displays. But in geometry, we can have all these things, but we also have diagrams. Of course, in algebra, you can have some diagrams, but geometrical diagrams are different, yeah. And maybe we have more of diagrams in geometry rather than in algebra. All what I said so far is just a very traditional view on what algebra and geometry are. So the case study we are going to discuss today is from current mathematics, in particular geometric group theory, and I will try to contrast it with combinatorial group theory. And these two are more like approaches to group theory. Two approaches. One is combinatorial and one is geometrical. Combinatorial is a traditional approach, whereas geometric is a relatively new approach. It begins with a famous paper by Mikhail Gromov, a Russian mathematician now, French mathematician, with his publication of a paper, Hyperbolic Groups, in 1987. So you can see it's a relatively new area of mathematics. Here is his website. This photograph usually appears when you Google him, and he has a very long list of. These are just groups of publications he published. So you can take a look what he has done, but what he did, he has an Nobel Prize for his revolutionary contributions to geometry. So the case study is supposed to be quite serious case study. Why revolutionary? I borrowed this slide from presentation by Jean-Pierre Bourguignon, devoted to Misha Gromov's revolutionary contribution to geometry. And he gives a list of revolutions in geometry. The first one is Chinese geometry, because the latest historical findings show that Chinese 9,000 years before Christ already had Euclidean Pythagoras theorem. If not proved, but at least they had some diagrams of Pythagoras theorem. And then, of course, Euclidean geometry is a crucial step in the development of geometry. Descartes' analytic geometry. I hope you know what it is. It looks very simple. You just transform Euclidean geometry into terms of coordinate system and write down everything in terms of algebraic equations, and you just use the algebraic machinery to solve these equations. However, Hermann Weyl said that introduction of analytic geometry was an act of violence. So it was really a crucial change in our geometrical thinking, compared to a huge step from Euclid's geometry to analytic geometry. Huge step in mathematical reasoning. And then Gauss introduced intrinsically curved spaces. So he proved that some surfaces don't change the curvature if you embed them in different spaces with different curvature, which is quite surprising. And then, sorry, I have to go through this very quickly, but you can always read it online. Then, appearance of non-Euclidean geometries, of course, was an important change in geometrical thinking. Nikolai Lobachevsky, Janusz Boya introduced hyperbolic geometry or negatively curved geometry. And then Riemannian geometry with a positive curvature. And also then, due to, again, Russian school, in particular Alexander Alexandrov, some irregular spaces were introduced as a new subject to geometrical study. So these are spaces with irregular curvature, let's say. I cannot develop more on this, but it's something more irregular than we used to have before, like in Euclidean geometry. And what Gromov did, he just pushed this idea further, much further, and he suggested even broader generalization of what Alexandrov did, and he suggested that we can treat irregular things as regular, very irregular things as regular, and collect concepts which have nothing in common. I will show you how he did it. So, a received view is that groups are typical algebraic objects. Right? However, Gromov suggested that groups, not only Gromov but other people did, but some crucial things are due to Gromov. Groups can be represented as geometric objects and studied by geometric methods. So this is the revolutionary step in the development of geometry. What is a group? A group is a set of elements with a binary operation, which satisfies the set of axioms. We did discuss it last time, so these are very simple axioms, but nothing so far you can see which connects it with geometry. So, yes, a binary operation with axioms closure, associativity, identity, and inverse. And I gave you some simple examples of a group. For example, a group of integers under addition 1 to 3, and identity is 0, and inverses are minuses. -1 is an inverse for 1, -2 would be an inverse for 2. So integers under addition is a simple example of a group. Another simple example would be symmetries or transformations of an equilateral triangle. You can either rotate a triangle to 120 degree clockwise or anti-clockwise. So clockwise rotation would be one of the group elements. Anti-clockwise rotation would be an inverse to this element of the group. And of course this rotation would preserve the shape of the triangle, therefore it is an element of the group. And also we have reflections, 3 reflections. So these transformations preserve the shape of the triangle, so they are elements of the group. And we have an identity element, so we keep the triangle unchanged. These are 2 simple examples of groups. In terms of cognitive representations, algebra is mostly manipulation of symbols. What you do, you use letters, you use signs, you can you can write down letters, you can write down words of signs and then sentences by using the equation sign, for example. And you can transfer letters from one side of equation to another. You can also use tables. You can represent a group by the table. For example, A and B could be 2 generators. Let's say reflection, one is reflection and one is rotation of an equilateral triangle. And you can write down all your transformations of the group in this table. There is another interesting thing. You can, if you have a graph, for example, in graph theory, which is also a part of algebra, you can present a graph. This is a well-known Peterson graph. You can present a graph as an adjacent symmetrics. So, briefly speaking, you can write down the relations of the vertices in terms of zeros and ones. If a vertex is adjacent to another vertex, you put 1. If it's not, you put 0. It's just it's simple, and then you can calculate. You can use computers to calculate these matrices. To use these matrices in your mathematical algebraic computations. It's not necessary to get into the details how it's done. So far you see in algebra cognitive representations are manipulations with symbols, and here is a citation from Immanuel Kant. But now let the geometer take up this question. What a geometer would do. First of all, a geometer would use Cayley graphs, which are due to Arthur Cayley and his friend James Sylvester, who used Cayley graphs in connecting algebra to chemistry. In order to draw a Cayley graph, you need a generated group. as I said before, in the previous lecture, for example, you need, in a group, you can find some elements which can generate all the rest of the group elements. Yeah, for example, as I said, in our group of integers under addition, you can use generate in set 1, and from 1 you can generate all the rest of the elements, for example 4 or other integers. Given a generated group, we can draw a Kelly graph. So here is a Kelly graph of Z, and the addition, the vertices are the elements of the group, so they are integers, and the edges are application of the group operation, which is +1 in our case. So, all right, we can draw Kelly graphs. Of course, I have to say that a Kelly graph is just a partial representation of the infinite graph. I mean, let's say, a Kelly graph is a mathematical representation of a generated group or a group, but the drawing of it is a cognitive representation. And of course it's partial, because the group is infinite. The graph, the drawing is finite, so it's only partial representation of an infinite graph. Okay, we have, now we can draw Kelly graphs, we can look at them, at their drawings, and maybe we can observe some interesting properties, like last time we were talking about the symmetries of Kelly graphs, that all the vertices are the same, doesn't matter how you label your Kelly graph, it will preserve the structure. And then maybe you can study these visible properties and compare them to algebraic properties of the groups. And that's how you can develop group theory, and maybe you can solve some combinatorial problems by means of Kelly graphs. And this is already geometry. You could say, oh, Kelly graphs are simply graphs, but when we are looking at them, we consider the structure, the visible structure of the graphs, which is common for them. Let me explain it more. For example, remember this graph. This is a Kelly graph, which we just hang by one vertex, and which helps us to see the growth of this graph. What I mean by growth, when you make one step away from the chosen vertex, you can count how many vertices you have away from one step away from the chosen vertex. So this is a function which dependent on the number of steps you make away from the chosen vertex. So f from 1 equals 4. Yeah? 1 is one step away. And f of 2 equals 6. Yeah? And then f of n, take some abstract n, would be a number of vertices of this group G, such that the distance between the chosen vertex G and some vertex L, which is less or equal to n. So this is the number of vertices which you have so far away, n steps away from the chosen vertex. Is it clear? Yeah. So, for example, if n equals 3, you make 3 steps, 1, 2, 3, away from the chosen vertex, and you count all the vertices you have so far. This is the function of the growth of the graph. And then you can try to think what kind of, what types of growth you can have. It turned out that you can have a polynomial growth. It's when the function is growing proportionally to some polynomial, yeah, or it could be exponential growth. So the function is growing exponentially. Presumably, the first one is slow and the second one is much faster. There were also things in between, and then you can relate this property of the growth of the graph with algebraic properties of your group. Gromov proved an important theorem that every finitely generated group of polynomial growth is virtually nilpotent. So, roughly, that if a group is growing slowly with a polynomial, in a polynomial way, it's virtually nilpotent, which is close to a billion. So it's not so big. Yeah, but you don't need to understand the meaning of the theorem. What is important is that from these instruments, generated groups, Cayley graphs, you can observe some new properties and you can connect them to the algebraic combinatorial properties of the group. And that's how you can develop group theory. But there is one obstacle. Ta-da! There is a problem. And the problem is you can notice that you can actually generate the group Z by choosing in several ways, choosing different generating sets. In the first case, it could be 1. You can generate it also by 1 and 2, or by 2 and 3. Yeah, 2 and 3 can generate you all the integers. When you draw Cayley graphs, they look different. Yeah. So when you prove your theorems about properties such as groups or growth of graph, for example, and other, the generality is distorted. The generality is under threat because what you are saying depends on the choice of generating set, right? How to get away with this problem? Well, try to do a thought experiment. Think what happened if you run away from your Cayley graphs, if you fly away from your Cayley graphs, from the drawings to infinity, but you preserve the plane unchanged. What will happen? Well, when you look at them from the distance, the structure is roughly the same. The structure is roughly linear. They are not. Of course, they are continuous. Yeah. Again, they are infinite drawing. They're supposed to be infinite drawings. The graphs are infinite. So you have to imagine them long enough. This and this and this, and from the distance. From infinity, you can see they have the same linear structure. So roughly the structure is the same, and you can talk about Cayley graphs up to this rough structure. This idea, of course, was mathematically shaped in precise mathematical terms, namely by introducing the notion of quasi-isometry. The idea is that you have two metric spaces, let's say, two graphs. Yeah? You have two graphs, and you can map one Cayley graph into another Cayley graph. But what is allowed is just some limited distortion, and this distortion has an upper and lower bound. Yeah, the lower bound would say you can shrink the distance between some x and y by some constant a, and subtract b. So you can stretch it a little bit, and you can subtract some constant, some limited constant. And the upper bound would be the opposite. You can shrink it and you can expand it and you can add something. And this is what the formula said. The image of this quasi-isometric function, the distance between two images shouldn't be bigger than when we multiply the distance between the two given numbers in the first graph. Yeah. So here is A, and we can add some B here, and it can be bigger than, should be less than if we subtract some B and we divide by A. So it allows some distortion, but not a huge distortion. This is the idea of preserving the so-called large-scale structure of the graph. So whatever we say about our Cayley graphs should be within these limits. When you have a geometrical object, for example, a geometrical figure, it's clear, you can stretch it and you can move it a little bit. But when it's a graph, what can you do with a graph? What does it mean, quasi-isometric mapping from one graph to another? Well, here you have a Cayley graph of F2, a free group on two generators. You can see that it has two generators. Let's say this is an identity element in the center, and step to the right is one of the generators. Step up, vertical step is another generator, and of course they have inverses. Yeah, negative sort of steps. So this is a group of two generators drawing, and this is F3. So here you have three generators, but from the distance they have the same structure. Up to quasi-isometry, the structure is roughly the same. This is an example to demonstrate you what could it be. Rough structure. How can you do this? You can simply collapse at each vertex. You can collapse one edge in F2. I put them in blue. So let's say you have X here and Y here. Two vertices, this and this. The distance between them is 2, right? 2 steps. If you collapse this edge, you will have this kind of situation. And at each vertex, if you collapse one stage, you will have this kind of situation. And it's all like fractal, it's all the same. At each vertex is the same, so it's growing in the same way. You can exercise your imagination, and you can see that if at each vertex you collapse an edge, you will have this kind of graph, precisely this graph, right? And this is quasi-isometry, because here you have a distance 2, but here it becomes 1. You only subtract one edge at each time, so it's limited. It's within the limits. So what do we learn from these thought experiments? Well, we learned that Cayley graphs of a group G have the same large-scale structure. And this structure is independent on the choice of generators. And therefore, it is the structure of the group itself. Right? So we solved this problem with generality. Generality is distorted. We can carry on with this approach. But it's not the end of the story, and the thought experiment goes on. And we can ask ourselves, what if we zoom out from the calligraphs in general? In general, I mean not only calligraphs of one particular group, but we can consider other calligraphs and compare them. If we look at them from the distance, for example, yes, that again, from the distance it looks like a line. And what is line? Line is a metric space R, right? So it gives us an idea that we can compare our groups with metric spaces. So again, this is that the dots should be connected. Z is similar to R from the distance, and if you look at Z square, which should be agreed, vertices should be connected in the calligraph, is from the distance look like a plane, like a Euclidean plane, which means that we can compare Z with Euclidean plane. So groups can be seen as metric spaces. How about other spaces? For example, hyperbolic spaces. Well, if you look at F2, the calligraph of F2, from the distance, it may look like it looks like a hyperbolic space. So on the second drawing, you can see that this group is placed on the Poincaré's disk, Poincaré's model of a hyperbolic space. And so therefore the graph from the distance look like a hyperbolic space. This is what we see from zooming away from the drawing. They look similar. Right? So the idea is to compare groups with metric spaces. What metric is? Metric is just a function, a distant function, which helps us to measure distances. In Euclidean plane, it's just a straight line between two points. But when you have some curvature, if you have some curvature in your space, it's not anymore the straight line. Yes, it's the shortest path, but it's the shortest path between the 2 points, but it may be not a straight line. Yeah, not always you can travel on a straight line. So we can introduce metric on some set, for example, a set from a group, a set of group elements. It's possible to that, and we can measure the distance between words in a group. Yeah, given a group with one generator A, we can write down all the words A, yeah, and the distance between this word and this one would be what? If we take one word, multiplication by a group element by generator as a unit length, what will be the length between these two words? It's 4, right? The distance is 4. In order to get from A to A, you need to multiply A 4 times by A. Or in order to get from this word to this, you have to multiply this word by minus A, A to the power of minus 1, A to the power of minus 1, A to the power of minus 1, and again. 4 times. So the distance between them is 4. But this is metric, strictly speaking, by definition on the group, and therefore a group can be considered as metric space. However, there is not much you can do with this metric. It's not so interesting. However, we can introduce it on Cayley graphs. Yeah? And in terms of Cayley graphs, the unit distance would be one edge, the length of one edge. And despite we can draw Cayley graphs in different ways, on the drawing we see that the edges have different lengths. Actually, it's the same length. Yes. Is it clear? That all the edges of the graph actually have the same length. And let's take this length equal to 1. Therefore, we can measure pass from one vertex to another. So from this vertex to this, it could be the length of the path is 2. Yeah? 2 steps. Yeah? And from here to here is 1, and from here to here is 1 again. So it's not that any path is considered, but the shortest path, the geodesic, so-called geodesic. Well, now when we have a metric on Cayley graphs, we can think how we can formalize this intuition we've got from thought experiments, zooming away, and how we can, strictly speaking, talk about hyperbolic Cayley graphs. Yeah. How can we formulate it in mathematical terms? Well, hyperbolicity is usually determined in terms of triangles of the space embedded in this triangles embedded in this space with a different curvature. If the space is positively curved, the triangles are kind of flat. Yeah, the sum of the inner angles of the triangle in this space is more than 180 degrees. In Euclidean space, it's 180 degrees. In hyperbolic space, it's less than 120 degrees. However, we have a graph. We don't have angles in our graph. What shall we do about that? Well, if you look at this hyperbolic triangle, so in the hyperbolic space, all the triangles are slim. If you look at these hyperbolic triangles from a distance, again, from, let's say, you run away from them up to infinity, they would collapse into such kind of tripods. So they would become slimmer and slimmer. They would lose weight up to they become extremely slim. This is again a thought experiment, but how to formulate it in mathematical terms. Well, we can get away from angles, and we can notice that for hyperbolic triangles, there is such an interesting property. Imagine that this circle is just an edge of a mug. I have a glass here, but imagine this is a coffee mug. Yes, and a hyperbolic space would be the surface inside this mug, right? And imagine that a triangle, the vertices of the triangle stick the edge of the mug. Yeah. But the triangle itself, let's say it's heavy and it's made of rubber, and it sinks down to the bottom of your mug, inside the bottom of your mug. What happens to the middle points of the sides of the triangle? Well, if you look at the Euclidean triangle or positive curvature triangle, the middle points of the sides would run away if the triangle is growing. Yes? But in hyperbolic space, these points would not go too far from each other. And in fact, it turned out that they would stay within some delta, some constant delta. And this delta is a constant for each hyperbolic space. So hyperbolic triangles stay slim even if their size is growing. So all triangles in a given hyperbolic space have this property of delta slimness. Yeah? So, in other words, each side of a hyperbolic triangle stays in a neighborhood of the union of the other sides of this triangle. And this is the property we can apply to our graphs. So we can, despite it's a graph, we can introduce the notion of triangle in our graph. We can say that any two arbitrary vertices in this graph would be vertices of a triangle. And the sides would be the shortest path between each couple of vertices. So this could be seen as a triangle. 1, 2, 3, 3 vertices, and the side which connects these two vertices would be this one. The side which connects these and these two vertices would be this one. And the third side would be this one. If you think of Z, the Kelly graph of Z, you can find some triangles there as well, and they will be zero slim because they all degenerate. So therefore our group F2, the free group, actually consists of such triangles, and all of them are zero delta slim. So all the triangles in this graph are hyperbolic, and therefore we can treat our Kelly graph of F2 as a hyperbolic space without talking about angles. Just use the notion of zero slimness. So what we learn from this thought experiment? First of all, up to quasi-isometry, and this is a crucial restrictment, we can now talk about the Kelly graph. We can ignore that we have to choose a set of generators. And therefore, quasi-isometric groups, meaning that they have quasi-isometric Kelly graphs. So now, not only can we consider different graphs of one group, but we can consider clusters of groups which have similar Kelly graphs. Similar, I mean the same large-scale structure. So now we can study clusters of groups, and we can talk about geometrical properties of types of group. So we can talk about classification of group. And then one step further, which we learned from our thought experiment, groups can be quasi-isometric to metric spaces. So we can take clusters of groups and compare them, these groups, with well-known metric spaces, Euclidean space, hyperbolic spaces, and we can use the geometric machinery we have to study these well-known metric spaces, especially hyperbolic spaces. Geometry is extremely rich. We can use all this geometry in order to study our groups, algebraic groups, algebraic properties. We can connect algebraic properties of groups with geometric properties of metric spaces. This is what we have learned from these thought experiments. concerning hyperbolicity, for example, we can see that groups with hyperbolic Cayley graphs are hyperbolic groups. And now we can relate geometric and algebraic properties. For example, hyperbolicity gives us quite a list of properties. Let me show you. Okay, this is a list of properties. How to zoom in? I cannot zoom in here. Well, this is actually mathematics, and I lost it. The idea is that there is quite a long list of properties of hyperbolic groups, which you can learn. And for example, a hyperbolic group contains a copy of a free group F2, and we have seen that F2 is quasi-isomorphic to F3, and you can show in the simple way Fn, therefore. So basically, we already have a cluster of free groups. We know that they are hyperbolic, and we know that hyperbolic group has exponential growth. So we can connect hyperbolicity with the growth function. This is already an important mathematical result. And you can see that the list is quite big. So it turned out that despite we neglect these fine details in geometry, and we concentrate only on large-scale geometry, the results we gain from this neglection are quite serious, quite useful. And here is just a short list of some mathematical problems which were either solved, namely combinatorial problems from geometric group theory, which were either solved by means of geometric approach, or they got some substantial progress in this in solving them. So the results so far, what we did, we were simply visualizing groups and then experimenting with these visualizations. We were zooming in and out, and then we gained some interesting results, such as crossing borders between areas of mathematics and linking domains, making new concepts available, which were unavailable in combinatorial approach, and then also solving some long-standing problems. What we learn also is that groups can be studied as geometric objects, for example, hyperbolic metric spaces. Jeff Chigger said that Gromov introduced ideas which forever changed the way a discrete infinite group is viewed, and his geometrical approach rendered combinatorial ideas much more natural and powerful. So this is about the significance of this result. We also have concepts which traditionally were considered geometrical, now can be applied to algebra, groups in particular. Well, metric, yes, you can introduce metric to groups, but not much you can do with this metric unless you use Cayley graphs. And you can apply hyperbolicity to groups, and you even can see triangles in groups. Finally, the new concepts appear and new instruments. Calligraphs. Well, yes, calligraphs were introduced in the end of 19th century. However, only now they received such an attention and became such a powerful tool in mathematical discovery. We've got a new concept, quasi-isometry. As you can see, quasi-isometry is similar to isometry, but isometry preserves the distance, whereas quasi-isometry preserves the distance only up to some limits. And we've got a new concept, delta hyperbolicity. It's not that it wasn't unknown before geometric group theory, but it was not really applied to algebra, especially it wasn't really applied before to such an abstract, such a discrete object as algebraic group, for example, or graph. So now how everything, all this has been done. The question is how. Yeah. There is a presentation made by Jeff Chiger about geometry of Misha Gromov, and the presentation, his talk was called "How Does He Do It?" How does he do it? All these tricks. How does he combine algebraic things which are uncombinable from the first glance? How is he coming to this insight? Jeff has his own point of view on how he did it, and this is mostly a mathematical point of view. But I'm suggesting a philosophical answer to this question. What I am saying is how to study groups geometrically. The answer is first, by changing the cognitive representation, and second, by running a thought experiment. That's how it has been done in practice. Or let's say that is how it can be done in practice. I am not saying that Gromov did it exactly in this way, so I don't know, but at least that's how it can be done. Indeed, what happens so far? The first step was, of course, a mathematical representation of a group. We can take any group and we can represent it by a generated group, up to a choice of generators. Yeah. This is a mathematical representation, but it doesn't give us much of freedom, and we introduce a calligraph. So a calligraph is again a mathematical object, and it is a mathematical representation of a generated group. Here we come to a change in cognitive representation, because there is not much we can do with we can write down the elements of the group, but there is not much we can do about it, and there is not much we can do with this abbreviation of a group. However, a mathematician would say that a generated group or a calligraph are basically the same objects. There is no much difference between them, although one is maybe group theoretic, a generated group is a group theoretic notion, and a calligraph is a graph theoretic, group theoretic object, but there is no huge difference between them. However, a calligraph allows for a drawing And here, with this drawing, we can do something else. And in particular, we can do a thought experiment. We can zoom away from a graph, we can notice some similarities with a straight line, and then we can formulate in strict mathematical words what it could be, namely we introduce the notion of quasi-isometry equivalence. But there is not, and then we can introduce metric space. So the crucial step has been done here when we visualize the Cayley graph. Since we have it visualized, we can do something about it. For example, a thought experiment. But if you zoom away from a cognitive representation of a group or even generated group, it doesn't give you this picture. It doesn't give you this intuition, doesn't give you this insight. So my answer is you have to change the cognitive representation, and then you can do something about it. You can run a thought experiment, which gives you a new knowledge. Gromov himself, this is a quotation from Gromov. What is he saying? In the first couple of sentences in this quotation, he is saying, yes, you can introduce metric on a group, a word metric, but it's not so interesting. It appears boring and uneventful for a geometer's eye, since it is discrete, and the traditional local topological infinitesimal machinery doesn't run on this group with metric. To regain the geometric perspective, one has to change his or her position and move the observation point far away from G. Then the metric in gamma, seen from the distance d, becomes the original distance divided by d, and for d going to infinity, so you run away from the graph to infinity, the points of G coalesce into a connected, continuous solid unity, which occupies the visual horizon without any gaps or holes and fills our geometer's heart with joy. So I think my story and my explanation how it can be done doesn't really distort Gromov's point of view so much. Although, of course, Gromov is a mathematician, and he is presenting his results mathematically and for mathematicians. I am trying to give a philosophical overview how it can be done. So, although he is saying that he runs away from the group elements with the metric, what he is actually doing, I think he is trying to zoom out from the Cayley graph. Cayley graph is already a mathematical formulation of this thought experiment, but how it can be done in practice, that's how it can be done. You change a mathematical representation first, but you choose such a mathematical representation which allows you for interesting cognitive representations. And as a graph, with a graph you have more freedom. You can do more things in your imagination in particular, and that's how you gain the insights. So when some philosophers notice that thought experiments often appear with visualizations, that's why I put a small I on my slide for you. I think we can come up with some story why it is so. Well, it is so because a set theoretic cognitive representation, or let's say adjacency matrix, or any cognitive representations which is traditional for combinatorial approach, wouldn't allow for such manipulations as we can do with graphs. And also a generated group didn't give us this opportunity, whereas the graph does. So I think this is kind of a story why, an explanation why visualizations often appear in thought experiments, because as soon as you have visualizations, you can do something about it, and you can add some physical properties and physical manipulations over these visualizations. You can imagine a visualization as a physical object, whereas when you have a pair of signs or letters, it's hard to zoom out from letters or imagine them in space or having them weight or being rigid or stretched. We have to do some checklist. At the beginning of the talk, I said that what we have to do, what is the aim of this presentation is, first of all, to show the significant role, the possible significant roles of thought experiments in mathematics, but also we have to check that this is a mathematical thought experiment, because remember, Norton would say these are simply hidden arguments visualized in some nice picturesque way. So the first question is this an experiment or purely analytic step? So Norton would say that no, this is just a hidden argument, and you can actually say, simply thinking in a logical way, well, we have these objects, groups, they are combinatorial objects. Why don't we study them geometrically? Why don't we look at them as geometrical objects? And of course, historically, groups were connected to geometry. Before you can use groups in order to study symmetries of geometric objects, for example. But here, in this case study, of course, the sense is not that trivial. So groups can be studied as geometric objects as such, as geometric, as metric spaces, for example. Right? And I think this is an experiment, because you're not doing any logical derivation here. You're breaking the rules of how you can categorize, how you place the subject of your study in the map of your research. So groups traditionally considered as algebraic objects, but here you are changing these rules, and in particular you are changing the rules of how you use visualizations, right? Because if you follow the rules, the traditional rules how to use visualizations, you would draw a graph, you would draw a Cayley graph, and you would supposed to use these visualizations how graph theory is supposed to use it. Zooming away from a Cayley graph, preserving the plane the same, is definitely not a traditional way of using visualizations in graph theory or group theory or mathematics in general. So this is definitely experimenting. Yeah? Second question, is it experiment or visualization? Some would say, well, yes, okay, it's not an argument, but it's just a visualization. It's not really experimenting. But I think it is experimenting, because, as I said, a visualization is is basically flat, or yes, you can do it in three-dimensional, but here you add some new properties. You place your graph in 3 dimensions, but you preserve the plane unchanged. So basically the graph is flat, 2-dimensional object. Well, graph actually has no dimensions, yeah, strictly speaking. As a mathematical object, it has no dimension. But visualization is 2-dimensional. However, in your experiment, you use another dimension, the 3rd dimension, and you run away, you zoom out in this 3rd dimension from the flat drawing. So I think this is experimenting with visualization, which is a representation of mathematical object. Then the 3rd question, is this a thought experiment? I mean, somebody could say, well, you draw a graph and you simply take your picture and you look at it from the distance. But maybe it's not enough. I mean, it said you have to look at it from infinity, yeah? Or the distance should be big enough. And strictly speaking, if you look at it from infinity, your piece of paper won't be visible. It would be a point, maybe. The whole plane will be just a point. So you really run into this thought experiment in your imagination. You have to preserve the plane unchanged, but the graphs the graph run away from you. So yes, this is a thought experiment. Is this a mathematical experiment or a physical experiment? Because it involves some physical properties. Let's say the 3rd dimension and moving away. Yeah, the motion. It involves motion as a physical property here. Yes, I think it's a mathematical thought experiment because we are talking about mathematical representations, graphs, and they have mathematical properties, and we do some mathematical assumptions, such as preserving the plane unchanged. This is how we choose the setting of our experiment. And this is determined by mathematical data, mathematical task. So this is a mathematical thought experiment. So let me wrap up the lecture. What we have done so far. So the task was to give an example of a mathematical thought experiment which has a significant epistemic role, and also which is non-trivial in terms of mathematical importance. So we did it by contrasting mathematical and cognitive representations and algebraic and geometric approaches, and we observed how they function in a case study from modern mathematics. And now come to conclusions. So we can conclude from this case study that a change in cognitive representation can make a thought experiment accessible. Together, visualization and thought experiments can play a significant epistemic role by making new concepts, resources, and perspectives available. I have a reference on my paper where I put these results so far, geometric, which I published in Filosofia in 2012. So you can take a look. if you want more details. And I wanted to discuss just a couple of things, introducing a couple of slides about using a case study in a philosophical research. So why did I choose this case study? I think it's a good example because it gives a sharp contrast between algebra and geometry, or at least between two different domains in mathematics, at least of rather two different approaches, combinatorial approach and a geometric approach. Also, I think it's an interesting example because it's from very advanced mathematics, it's from current mathematics, and also it's significant. As we can see, it played some revolutionary role in development of geometry, mathematics, and at the same time, what I managed to deliver so far, I think it's quite accessible for a broader audience. So I hope you are able to understand mathematics at least up to grasping the philosophical points. Again, concerning methodology of using case studies. So the idea is, as at the first lecture I was talking about this new approach in philosophy of mathematics, namely the philosophy of mathematical practice, which tries to build a rich collection of case studies from mathematical practice. But also the question is how to choose case studies, and also what questions are amenable for using case studies. What questions we can answer by using case studies, and which questions we cannot answer. So I think definitely these case studies we discussed in our lectures did shed some light on mathematical reasoning. At least we could see how actually it may be done in practice, gaining interesting mathematical results, significant mathematical results. And also, I think this case study did show that epistemic roles of thought experiments and visualizations can be significant. Not only pedagogical, not only illustrative, but also connecting domains and giving new, interesting ideas. Very fruitful ideas to mathematical development. So I think at least from epistemological point of view, case studies can be very useful in philosophical research. And I would be very happy if you give me your feedback and your ideas how the case studies methodology in philosophy of mathematics could be improved, how it could be developed, what questions we can approach by means of case studies, what could be our methodology of choosing case studies, and how we can develop this point of view, this technique. Yeah, that's it. The end, of course. Thank you. What if we just have questions, discussion, and then finish for today? Is it all right? So, please, anything you would like to ask? Maybe some comments, maybe some ideas?
Yes, I would have a remark on your slide about geometrical revolutions. I missed projective geometry, because the idea of projective geometry is having this point of view from infinity. and it gets with the idea of graphs, as you were saying. Like for Peterson graph, we can imagine a pentagon and another pentagon here and a projection relation. And in projective geometry, you have no distance, no metric distance, you have no angles. So I think projective geometry in the history of mathematics would be important perhaps for this approach to graphs. So
that's a great remark. Yeah, thank you so much. I think, yes, definitely. Oh, thank you.
And I would also have a doubt, because when you show like groups that have a line representation, so for instance the integers, for any set generator, when you zoom out you have something as the real number line, right?
Yes.
But I was thinking about rational numbers and real numbers. Like, as Cantor showed, they have different structures, right? But when I zoom out, I would have the same line, but I know that they don't have the same structure, like rational numbers and real numbers, right? Don't I miss something with this large-scale geometry representation?
Yes. Gromov has this point in one of his papers, and yes, he's saying somebody would ask, don't you miss so much when you discharge, when you ignore all this fine structure? Yes, you do miss something, definitely. But in fact, and he's saying this in his publication, in fact, it turned out that even if you concentrate only on this very rough, large-scale geometry, it turned to be extremely rich. So the geometric group theory developed into a very prosperous domain in mathematics, and now it's really blossoming. And they proved many interesting theorems. They solved some problems which were long-standing problems in combinatorial group theory. The thing is, as I said, hyperbolic geometry is very rich. It's a strong instrument which can be applied to solve combinatorial problems. So yes, you miss something, but you gain a lot.
Okay.
More questions? Was it accessible indeed, this material? How much did you able to understand? Were you able to understand in Gromov story? Quite a bit. Yes, in general. It's very advanced mathematics. It's not that every mathematician understands what's going on. But I'm very happy that I found this example, because somehow up to some level of complexity, the broader audience can understand the general idea, and especially the revolutionary idea. More questions? Comments? Remarks?
I think it's interesting to see what he said about what you miss when you do that. Because you see that different ways of thinking takes you to different possibilities and capacities. For example, just a commentary, I don't know. As you know, I study Arabics, and on Islam, you see those carpets with those bedrooms, those big bedrooms, and Islamic thought is really different from Christian thought. Like, if I would try to explain some parallel, as Christian thought would think of the divine in the individual, Islamic thought would think of the divine in the social whole, as a whole, as if you see those patterns, mainly the lines that form those patterns are irregular, and they go, if you take one along, it's a chaotic line, but they form a beautiful pattern with chaotic lines, as if you take the life of a person, it can be chaotic, and as a narrative it can be anything. But if you could zoom out from the whole of the history and the social experience, it would be a pattern, and an harmonic pattern that would be the divine. And this is an ancient thing, it's a philosophical thing of the Islam. And it seems, it came to my mind that this is something that could be brought to rationalization, I don't know, to a more formal way of considering this type of philosophical thought, and to use it in mathematics, right? Just to don't be arrested in some formal laws, but to use this type of narrative visualizations and type of things to work with those formal laws and to see other things from that. I don't know if the comment.
Yes, yeah, thank you. Yeah, very beautiful remark. Thank you. And it looks like this zooming in and zooming out is a useful instrument in mathematical reasoning, because in this thought experiment we could see that you can zoom out from your calligraphs, but also when you need, let's say, you need to put everything in mathematical concepts, let's say hyperbolicity, for example. You zoom out from the graph and from traditional drawing of a hyperbolic space on Poincaré disk. You look at them from the distance, you can see similarity, the rough similarity. But when you have to formulate hyperbolicity on calligraphs in strict mathematical terms, you zoom in and you look very close to your graph, because you need to consider triangles, you need to consider the absence of angles, you need to explain how you are going to deal with this absence of angles, and what are the sides of your triangle in a graph. The delta slim and so on. So you really have to consider it from the close distance. And the combination of zooming out and zooming in is widely used in mathematics, I think, and it seems to be very useful. But this is beyond mathematical logical approach. If you say that mathematics is a proof-producing enterprise, you definitely lose all this beauty of what they're doing in practice, mathematicians, of the beauty, the richness of mathematical reasoning, which plays not only a pedagogical role, not only illustrative role, but plays an important role in mathematical rational progress. Yeah? Any more remarks, questions?
I think like a usual place to look for thought experiments are algebraic topology, and even theorems like the Poincaré conjecture that was proved recently. They have like a lot of thought experiments running on these places. Do you consider this area to look for some examples or some case studies?
Yes. If you remember in my first lecture, I showed you a book. I had a slide with a book by Richard Thurston, and many of his results from three-dimensional surfaces and topology were used in the proof of Poincare conjecture. So in his book he has quite a good collection of thought experiments, these topological type thought experiments. In particular, how to imagine surfaces, multi-dimensional surfaces, how to imagine these surfaces, which is hard for us to dimension. And he does use thought experiments, imagining yourself in a room in which walls are collapsed in one into another, but you're in between them, and imagine that photons are traveling from your eyes and reflect from the walls. Very interesting, extremely interesting thought experiments. And maybe you remember I had a photograph with Richard Thurston. He had a robe instead of a scarf on his neck. So when he was trying to demonstrate that it's very good if you try to imagine something, how it's going on in multiple dimension spaces. It's important. So yes, I did look at these thought experiments by Thurston. The only thing he uses them in order to illustrate, and but not only to illustrate. It's also important for developing the style of thinking, of mathematical thinking, topological thinking. It's to train your intuition, how to reason with these complicated objects. So I think they're also important. But I wanted a case study which sort of gives you good results, bright results, to show that thought experiments can be used not only as illustrations.